Okay, so let's talk about each of the factors affecting the rates of reactions now in terms of collision theory, because you have an understanding of collision theory. Now, I'm not going to talk about the nature of reactants because this is just the basic chemical properties where certain bonds are stronger than other bonds, and if they require more collisions, they require more energy, and if it requires more of those things, it will generally take longer to react, right? Let's talk about concentration. Let's talk about temperature. Let's talk about surface area, and then finally, let's talk separately about a catalyst. Okay. Now, the catalyst is going to be the difficult one for me because usually I have an assistant that helps me demonstrate this. But yeah, let's start with concentration. Now, if we talk about concentration, let's think about a molecule in which we have a water molecule and we have, I don't know, let's make it simple. Let's talk about sugar that's going to dissolve in water. Okay, where's my pen? Right. So I've got a container and I've got a vessel, and in my vessel I've got a bunch of water molecules over there. Right, right. And these water molecules, they have to react with, let's say, the sugar that we want to dissolve in that. So the quicker the sugar dissolves, the faster the rate of the reaction. Okay. Now, in order for these things to dissolve and to form this solution, what we need is we need the water to collide with the sugar. Okay. Now, it's as simple as this. The concentration is simply the amount of the substance. You can think of that. Concentration, you can think of it as the amount of the substance. Okay. If you were to throw a teaspoon of sugar in a pool versus throwing a teaspoon of sugar into a glass of water, which one would react faster? Well, the reality is it should react faster where there's a higher concentration of the water molecules. And the reason for this is think about the collisions, right? Think about the collisions as attacking the sugar, okay? So if I've got more water, of course, I have more water available to attack the sugar, and therefore there will be more collisions. Now remember, not every collision is what is known as an effective collision. Not every collision is known as an effective collision. So what we need is, we need as many collisions as possible, because the more possible collisions that you have, the higher probability that there will be effective collisions, right? Okay, and it will become clearer in a moment as we look at more examples. So that's number one. Okay, so let's just bring up a new sheet, change that. That's concentration. So if I have more water molecules available to react with the sugar, it will increase the rate of the reaction because more water molecules are attacking sugar per time unit. Okay, let's look at temperature. Now we've got a little diagram over here that shows you low temperature and high temperature. And what I want you to look at is I want you to look at these things over here. Right, just look at these things carefully. Do you see that? What are these? These are arrows, but the arrow there and the arrow there, they almost identical. The only difference is this arrow is longer, but this arrow and this arrow, they point in the same direction, right? There. Okay. So A and B, these are molecules, right? Sorry, these are atoms or particles. So A and B, these are reactant particles, and as you can see, this is a closed vessel. At a low temperature, we see that this arrow is quite short, and at high temperature, this arrow is longer. Now, what does the arrow represent? Now, if you remember correctly from our previous courses, it represents a vector. And this vector that we consider, it has both magnitude and direction. Now, as you can see, the direction doesn't change, but the length of the arrow changes. And the longer an arrow, the greater its magnitude. Okay? So here we are talking about how quickly these particles move. How quickly these particles move. A is moving in that direction, it's not moving very fast. A over here is moving in the same direction, but because its arrow is longer, it's moving much faster. Okay, what does temperature do? Temperature is directly related to what we call kinetic energy. And kinetic energy is the energy an object has or particle has due to its motion. The more energy the particle has, in terms of kinetic energy, the faster that particle will move, right? Or the harder it is to stop that particle from moving. But let us look specifically at this. And how do you imagine this? Remember, In order for A and B to get together and start what we call the activated complex, remember that is the stage in which they make a baby. The stage in which they make a baby. What we really need here is we need A to knock into B quickly. And if they do it faster, then the rate of the reaction will increase. Now, let's imagine that A and B are little children. A's are the boys and B's are the girls, right? Or whichever way you want to call it. And you want, okay, this sounds bad. Let's just imagine that they need to have collisions and stop there, right? So you have a closed vessel and you want, and you have kids running around. So in general, they're just running around. Think of feeding those kids with sugar. Give everybody in the entire room a whole lot of sugar, right? What will happen? They generally get hyper, they run around faster, they're more likely to knock into each other, and that just increases the probability of collisions, therefore increases the probability of the number of effective collisions. And that's really what temperature does to the particles. It gives them energy, and with that energy, they are more likely to collide because they move quicker. So, for example, if we look at B over here, B will inevitably knock into A. However, B over here will knock into A before B over here does it, right? B at a high temperature will knock into A much quicker. Okay, so if things sound a little bit hazy and vague at this point in time, please just rewatch the video, rewind, replay, because I do have a habit of speaking quite fast at times, right? Okay, that's what temperature does. It is like sugar, feeding it to kids in a closed vessel. Kids will run around much faster and therefore they will collide quicker. Okay, righto. And therefore you got a higher probability of collisions within the same time unit, therefore increasing the rate of the reaction. Okay, so let's just bring this up. So we've spoken about temperature, we've spoken about concentration. Let's talk about the surface area of a solid. Now, I don't have an animation for you right now. But on our online course, we do have animations from other providers that you can definitely watch, that I think will add to this playlist as well. Okay, let's talk about the surface area of solid reactants. Now, in South Africa, you know, we've got a very famous headache tablet, right? Really, it's a headache powder. And this medicinal item, it used to have a slogan called, "It works fast because it's powder." And what is that? What is that item? Well, it's Grandpa. Now, I'm sure today you get Grandpa capsules and tablets, but Grandpa is known for its powder form. And the reason Grandpa gets to work so quickly is because the powder can immediately dissolve due to this principle. The surface area of the solid reactant increases. So let me draw something out here. Let's just think about a calcivita tablet. Let me just check if I've got one. Okay, so it seems that I've got calcivita over here. And these items, these calcivita items, these are effervescents, right? Unfortunately, time doesn't allow us to go into detail to show you how this dissolves, but I think it's an incredible experiment for you to do. Take one calcivita or any effervescent, drop it in like this, measure the time it takes for the effervescent or the tablet to completely dissolve, and then also take one in which you crush it and break it up, and then you also measure the time in which it takes to dissolve. So let's just talk about how this thing works, right? And let's just get that video a little bit bigger. Okay, so I've got a bit of a larger video there. As you can see, this is an effervescent tablet. It usually gets dissolved or thrown into water. Now let's just talk about how this works for now. I drop this in water, and when I drop it in the water, remember the particles need to collide with the water molecules or the water particles, right? And when I drop this in the water, only the outer layer will react with the water until the outer layer dissolves. Then the next layer dissolves, and the next layer, and so forth. So it has to wait for the outermost layer for this to occur. However, let's assume that I break this, right? So now it's the outer layer that's going to react with the water molecules, right? But you also have this additional area that's also going to react and dissolve with the water molecules. Okay. Similarly, this area over here. So this is the principle behind it. If I continue to break it, I'm going to take this thing and I'm break it further. In the same time unit, this is also going to react with the water, that piece over there and that piece over there. So just remember, for the fifth a factor that affects the rate of reaction, it is that if I increase the surface area of a solid, it will increase the rate of the reaction, right? Due to this understanding. And to remember it quite easily, just remember, Grandpa, it works fast because it is powder. That used to be the slogan on the Grandpa TV advert. Okay.